Thank you so much, everyone. And I want to take a little bit of time now to talk about the impact of the energy storage industry. This was a lively discussion with some of the decision makers that are going to help shape markets and policies across the energy landscape. But it's important for us to take some time and really understand and account for why. Why are we doing this? What are the benefits of the advancement of the energy storage industry? What's the cumulative impact that we can expect? There's a transformation underway in the power sector. I don't think anyone disagrees with that. One that brings with it new technologies, smarter systems, and a more integrated understanding of the value that the grid delivers to our society and to our economy. It's happening right in front of us. More than 160 gigawatts of renewable energy was installed in 2016. In the United States, the wind industry expects 49 gigawatts more before the end of the decade. Last year alone, solar put in 16 gigawatts on the grid, or 15 gigawatts on the grid, my apologies. Top corporations aim to contract more than 60 gigawatts over the next 8 years. This is massive. By 2021, there's going to be more solar, wind, and storage capacity on the grid than there is capacity from natural gas. That is a really big shift for the industry. Economic conditions and competitive procurements will continue to push coal-fired generation off the grid across the United States. And while the supply of energy coming into the grid is changing rapidly, the demands we are putting on our aging infrastructure are also becoming more complex. 2 million EVs on the road already, and nearly 20 different models to choose from. Responsive buildings, virtual power plants are drastically changing load curves. Advanced industrial robots are churning out widgets faster than they ever have before. The electric grid is the engine that drives our economy. And as the United States moves away from an era of centralized baseload power, we are giving way to a more integrated platform where all assets can compete side by side based on the value that they provide to the customer and to the network as a whole. These seemingly disparate networks are really drawing closer together. We're seeing transportation, industry, data, and buildings. And each of these networks is being rapidly electrified, putting new demands and strains on our grid, becoming entirely interrelated and increasingly interdependent. And it's very interesting. Here's what that looks like. I found this absolutely fascinating. These are goofy little robots zipping around in a warehouse. They sort more than 200,000 packages a day. You almost have to ask, what is this human doing in this equation, right? These robots are picking up a barcode and they move about autonomously across this grid. They're commanded by a barcode to a destination and drop off packages. Entirely electric. And by using signals from a centralized station, they also have a way to know how much charging they need to do. This is when all of these networks come together, what that can look like. And it's so easy for them to be able to predict exactly the capacity that they're going to be able to need to handle and calculate how much energy they'll need based on the volume and timing of incoming packages. What if this warehouse floor were to expand to the size of a city? This scales up so easily. It's not hard to perceive of a future where a Hyperloop train moving freight and passengers departs from Pana Station, right outside of town here. Many of you went to visit it recently. It's a microgrid itself. It's powered by solar, reinforced by batteries. This grid-connected train will ferry passengers and cargo, modular, based on demand, sets off for a 1.5-hour trip to Los Angeles. As it departs, it sends a signal to everyone in LA, to a centralized station there, that calls for 177 EVs exactly to be ready for those passengers, light-duty trucks to pick up that cargo and take it to a destination. Pre-charged, the exact right amount, and with a signal from an app or from a barcode that tells them where they're going to be going. That is seamless. That's data, transportation, industry, all linked together by the grid, creating new dynamic demands 24/7, interconnected across vast geographies while still balancing localized needs. electrification will fundamentally transform the entire power sector. And this confluence of forces is putting us on a path to deploy more than 35 gigawatts of energy storage by 2025. That is a really large amount of storage from where we're starting today. That is a big change for the power sector here in the United States. And there are some vast benefits that come along with that. There are drastic cost declines. There are market and regulatory reforms. And most importantly, increasing recognition of the multifaceted value that being able to store energy can provide in all of its forms. The networks merging will produce more than 3,500 terawatt hours of new demand on the system, giving us the imperative to transform our thinking and how we approach planning for the grid. Independently, each of these networks we're talking about and describing has their own value. They have their own strengths, their own weaknesses, and unique capabilities and inefficiencies. And as each draws closer together, the electric grid becomes the nexus of all of these networks. But along with this convergence, we also are going to be sharing each network's shortcomings as well. With new technologies and innovative strategies, it is critical that we look at the shortcomings on the grid. It's not only possible that we address them, but it is also essential to society, and that we mitigate vulnerabilities and that we build more flexible, sustainable, and resilient electric grid. It is estimated that to overhaul our entire electric network from its current form with our current assets would cost us more than $5 trillion. And we have a choice. Our utility partners have a choice. We can either rebuild the grid with today's infrastructure and assets with incremental improvements, or we can invest in new technologies and invest in new strategies that can deliver better outcomes at a lower cost. We need a grid that is prepared for this electrified future. We need a grid that is disruption-proof. I believe that people will look back on the last decade of energy storage skepticism and realize they had framed a new paradigm incorrectly based on an old one. Today's paradigm of a grid driven by cost, predicated by balancing and infrequent peaks, is being turned on its head. For over 100 years, electric grids have been built with the assumption that electricity has to be generated, transmitted, distributed, and used in real time because wide-scale energy storage was not economically viable. But that has changed, and the grid is beginning to change along with it. The grid is built to minimize cost and to serve peak demands. Those are two of the primary ways that we look at the grid. The entire system, from power plants to wires to substations, all of this is scaled to meet the needs of the system during the infrequent but entirely predictable maximum system peaks that occur each year. These surges in demand happen less than 100 hours a year. That's barely 1%, but represent a substantial cost to utilities and ratepayers alike. In Massachusetts, the top 10% of demand makes up for 40% of the cost to ratepayers to run that system. In New York, the top 100 hours, as it's referred to, costs ratepayers more than $1.7 billion. That's an immense amount of money to serve less than 1% of the need of that system. These peaks represent one of the biggest disruptions to our grid. And this is critical because every disruption, big or small, comes with a cost. And this cost can be anything from a minor inconvenience to a risk to people's health and safety. Most networks that are important to our society, transportation, food, data networks, they combat disruptions by maintaining robust storage and reserves, usually on the order of 10% or more of daily demand. And this imparts flexibility to the system. This ensures proper capacity to meet customer demand when and where it is needed. And it prevents market spikes from any supply chain interruptions. And this is critical because every deviation from the mean, every inefficiency brings with it an economic burden. And in an electrified society, the grid is being exposed to a bevy of new disruptions. All of these networks can now disrupt what is happening on the grid. Let's start with the power itself. I think everyone's very aware of this. It's humming along at 60 hertz and a set voltage, a frequency that indicates a perfect balance of supply and demand. Every change, every new load, every new intermittency in generation, it requires an instantaneous and exacting response to keep that frequency in harmony. And this comes at a cost. Depending on time, location, grid congestion, all of these factors, today's grid demands consistency and lacks meaningful flexibility to be able to adapt to changes in system needs in real times. Spot prices can reach $3,000 per megawatt hour or more, and frequency regulation can be triple the standard price to address these small variabilities, so much more than baseload. Oversupply brings with it cost as well. Increasing solar is depressing midday power prices, and gusts of wind power at night are already pushing prices negative. Both lead to ramping down sluggish fossil fuel plants, causing them to operate inefficiently and increasing their emissions profiles. Now try and take that system and scale it up to handle the demands of an integrated set of networks. A network so vulnerable to disruption that an unexpected strong breeze can mean the difference between $30 baseload and $3,000 reserves. We can't work in a system like that. Our grid, without widespread storage, is strained to meet today's weather needs and is insufficient to meet the demands of an electrified economy. Think about this for a second. In an electrified transportation network of tomorrow, million autonomous EVs are based here in Denver, and they're out on the road. Imagine a traffic jam. Someone runs a red light, merges too quick, and now all of a sudden we have an accident on a highway. We have 4.5 gigawatts of load that is now stranded out on the roads. It could be delayed 10 minutes, it could be delayed 2 hours. We don't know. We don't know when it's going to be arriving. We can't solve this with traditional demand management. And these vehicles are going to be optimized in an autonomous network. There's going to be the right number of seats in the right number of vehicles spread across the system efficiently. Just like our little robot friends in the warehouse. They're going to be ready for customers when they need them. This is extremely convenient for customers, but it makes traditional balancing nearly impossible to predict with today's capabilities. You could try and put traffic patterns into Plexos. You could try and factor those things in, but gather more detailed data and information to help predict some of these changes. But data without the ability to act, without the capability to do something about it, is just a spreadsheet. We don't have the capability built in today. Energy storage delivers that capability to respond when and where we need it. In a future with more of our networks dependent on the grid, the power sector will inherit an intimidating array of new disruptions, just like this traffic jam. And therein lies the value proposition for pushing energy storage forward. This is a stabilizing force and buffer that can react to dynamic changes on the system. With the capability to deliver exactly the amount of power you need, exactly when and where you need it, that is a grid that is disruption-proof. This means markets can operate more efficiently every day. No more planning the grid in the fear of system imbalances and scaling every asset to peak as we do today. Over the next 8 years, with more than 35 gigawatts of energy storage installed, we will save more than $4 billion just in market operations, just from being able to run the system more efficiently. That is a massive amount, and that value continues to increase. And operational savings, systemic efficiency, that's really only half of the equation. And that is today's paradigm. We also need to account for the value of these new technologies. Those market disruptions are minor when we look at the physical disruptions that threaten the grid. Superstorm Sandy, Hurricane Katrina, polar vortex. When the grid is down and there is no power, lives are put at risk. Human health and safety for society is put at risk. Businesses are closed. Economies in these places are devastated. Now, even without any major storms, 2016 was not a great year for system reliability. There were nearly 4,000 blackouts in the US last year. About 18 million people lost power for 45 minutes or more, up almost 40% year over year. Weather caused about a third of those. Faulty equipment sometimes comes into play, caused maybe a quarter of those. My favorite is critters, caused a few of these as well, as I think everyone's aware. Plenty of squirrels, badgers, and snakes find their way into the grid and are able to knock down power. Most surprisingly, on one occasion in 2016, the grid was taken down by a mountain lion. So if you run into the gentleman from Eden and the folks from Eden, make sure to ask them about that one. This is from their blackout tracker. But disconcertingly, when we look at this full 4,000 of these blackouts that happened, unknown accounted for nearly a quarter of them, and almost 14% of unknown critters as well. With today's technology and a lack of two-way integrated communication, more than 20% of the time that the grid goes down, we have no idea why. You can't solve a problem if you don't know the cause. It wasn't long ago that utilities found out about power outages because they got a customer phone call, and that's how they knew that power was down. If we don't even know the cause, we can't address it directly. We have to build a system that is more resilient and more reliable to be able to address the massive impact of these blackouts and these losses. Every time the grid goes down, it comes with a cost. Analysts call this the value of lost load, which very predictably varies based on what is losing power. It is estimated that every year, outages, spikes, surges, cost the US economy more than $150 billion. Now, I'm not going to stand here and tell you that an energy storage system is going to defeat a hurricane somehow, or that we might be able to eliminate the impacts of weather the same way that we can eliminate the costs of grid variability by leveraging storage systems. But by taking storage spread throughout the grid, we can save billions of dollars. Between now and 2025, the 35 gigawatts of energy storage that will be installed will produce immense value for the system and will save more than $27 billion by increasing system reliability, reducing emissions on the system, and ensuring that we have a more resilient grid. This is a value that is not yet factored into any RFP and provides new capabilities for grid operators and customers that far exceed what system hardening or redundancy can. Energy storage redefines what it means to be reliable and resilient, and the benefits are immense. Regulators and grid planners are quickly recognizing this value, and this led to one of the most significant milestones in the industry last year, responding to the environmental disaster at Aliso Canyon. Many of you already know the details. Was a major leak in a natural gas storage facility in California. The CPUC sprang into action along with advocates and industry, and they called for the deployment of energy storage systems to address upcoming supply shortages, leveraging technology to mitigate this supply chain disruption in the gas sector. What is significant here is the response time. From RFP to flipping the switch in under 5 months, the installations themselves taking just over 3. That rapid deployment is unheard of in the power sector. Any other traditional asset would take years from planning, environmental review, siting, and the challenge that was being faced was immediate. We needed an immediate response to an immediate problem. And these systems, these energy storage systems, can address challenges anywhere on the grid. The environmental impact of a new system is negligible. no new emissions, no water impacts, and you can install these systems right downtown, and people would barely even notice. They would just see some boxes over there, maybe a small building. We have a new tool, one that can respond to grid emergencies in record time, proven, cost-effective, and available to us today. These benefits, operational cost savings, market efficiency, and the value of a disruption-proof grid are only 3 of the ways in which storage generates systemic value for our grid and our society. But there are plenty of headwinds in adapting our current approaches and current business models to this new, decentralized, and sustainable paradigm. What is needed to achieve these outcomes that I've described is a fundamental rethinking of how we invest in the grid, the criteria on which we make our decisions, and how we plan to meet our future needs. Today's grid needs consistency and simplicity to be efficient. And as we have just discussed, the demands of the electrified economy are anything but simple and consistent. We need to prepare ourselves for this nexus of networks, for all of these networks coming together. Our utilities, our munis, our co-ops, they fill such a big role, but they also serve as a place where we can invest collaboratively in the assets that make up our grid. And they will be some of the primary market drivers for the energy storage industry. It's estimated that more than 84% of the funding that will be in this industry over the next decade is going to be coming from third parties and utilities, helping to drive this forward. 35 gigawatts of energy storage by 2025 means breaking down the planning silos of generation, distribution, and load forecasting within utilities. Holistic planning, investing not predicated on peaks and cost, but driven by value and outcomes for the people who utilize the grid. Grid planning in an energy storage-enabled world brings with it 2 fascinating things that I want to highlight that have never really existed before. The first is flexibility in sizing and siting. Energy storage affords us the ability to add the right amount of capacity in the right place instead of having to purchase capacity in large increments with large power plants. Committing ratepayers to a 20-year-plus investment with those power plants that may not even be necessary or viable by the time it is turned on 5 years down the road. And second, and this is really the groundbreaking reason that storage is so important to our future planning, adding energy storage paired with generation is the first time that we have been able to add capacity while lowering costs. Today, if you build a centralized power plant, everyone has to chip in a few bucks on your system to cover the cost of putting that plant in. But with more innovative strategies and systems that combine storage and generation, or even just storage itself, we can add the right amount of capacity to the system and the value that is added. The enhanced performance, the increased reliability, the systemic efficiency, that can lower the overall cost for the system. That is unheard of until today. And that is something that really does flip grid planning and investment on its head. And if in 3 months or a year or 2 down the road, you see a drastic shift in system demand, that's fine. These systems are modular. Some of them are pre-containerized. You can back up a truck, pick it up, and move it to where you need it now. That is an immense ability to have a reconfigurable grid asset like that. If we don't embrace this integrated planning approach, we are going to create dueling networks with the same vulnerability to disruption that we have today. Innovative companies are going to keep driving these systems onto the grid. That is for certain. And storage is going to keep moving forward based solely on its value inside the fence, the on-site value of that system and a primary application. But if the value and the full holistic value of that system is not accounted for into grid planning, installations are going to inadvertently strand grid assets because we're not talking to each other about where to put these. And on the flip side of that, utilities are going to strand energy storage value There's just going to be value sitting on the grid that is not being taken advantage of. And in those scenarios, no one wins. This is the opportunity, what we are striving for, to install more than 35 gigawatts of storage by 2025. That is why it is more important than ever that we work together to keep building momentum, continued progress in California, and new markets opening in Oregon, Hawaii, Massachusetts, New Jersey, New York, and most recently Maryland is one of the most recent to add to that list. This is just the beginning, and there is a lot more work for us to do. And we do need your help. We need you to keep telling your stories. We need you to keep educating about the reality, where these systems are in the ground today, the value that they're providing. We need utilities and industry to be able to work together side by side to create one cohesive network, integrating all aspects of our economy, addressing the grid's vulnerabilities, and sharing all of its benefits. None of this would be possible without the continued dedication of innovative companies and industry champions. And it is important that we take time to recognize their efforts and their contributions to growing the industry.